This is Module 4, Lesson 1. Today we're going to look at forces. So getting started, very simply, a force is any push or a pull on an object. Now the units of force that we're going to be using are called newtons. I'm guessing that you could figure out who they're named after. It's a capital N. So when you see a number that has a capital N after it, that initial N does not mean north in this particular instance. So you would have 40 newtons north if you're going to have, both of those, because I've had some students get confused because we've been doing things like 40 meters north of east, something like that. This N will immediately follow your numbers. So when it does, it will stand for newtons. Okay. Another thing that you might see sometimes for Newton is that 1 Newton is equal to 1 kilogram times meter per second squared. So technically, you could say that 40 newtons to the north is 40 kilograms meters per second squared north. So those two are equal to each other. So a couple more things about forces. You have more notes this go around than things to do at the moment. There are 4 fundamental forces. We are going to look at the first 2. Those are the things that we are going to consider. You can see the 4 on your screen here. We'll study gravitational force. As you well know, that keeps us on this earth, keeps us grounded, literally. So we have already talked about gravity a little bit. For example, you know that gravity accelerates an object at 9.8 meters per second squared. Towards the very end of class, we'll be looking at electromagnetic forces. And then you have the strong nuclear force and the weak nuclear force. And just to give you some information, since we're not going to do it at all, but strong nuclear force is what keeps protons in the nucleus. If you remember your chemistry, or if you haven't had it, protons are all positive. And so for them to be together, they don't want to be together. They want to repel each other. And so the strong nuclear force is what helps contain them and keep them from pushing each other away. And then you have the weak nuclear force, which plays a role in the stability of the nucleus and plays a role in radioactive decay. But these are the 2 that we are going to focus on as far as the class goes. And then we'll focus on just forces in general, like between 2 objects. Well, I'll do like a whole unit on gravity. Okay, what we're going to get into now is Newton's first law. You're going to learn Newton's 3 laws, and we're going to start with this first one. It's a good place to start. So Newton's first law says an object in motion will stay in motion. There should be an in there. And an object at rest will stay at rest unless a net force acts on it. It's often called the law of inertia. So what that means is that in the absence of air resistance or in the absence of friction, if you pushed a rolly chair across the floor, it should just keep going forever and ever and ever and ever and ever and ever until it hits something. However, that's not what happens. If you've ever pushed a rolly chair across the floor, you probably know that it'll come to a stop on its own if it's got a clear enough path. Why is that? Because friction acts upon it and it keeps it from going further. And that's exactly what this is saying, that an object is going to stay in motion unless something acts to stop it. And if something's not moving, if you have that rolly chair that's just sitting there on the floor, with nothing pushing on it, then it's going to stay at rest until something pushes on it. An object's inertia is basically very related to mass, but it has to do with how difficult it is to change an object's position. If you're driving down the road and anybody's ever told you, like if you're, you see a big Mack truck pulling a big old trailer. I won't have my wheels properly on here, but you have an 18-wheeler, and then you've got like just, a plain old little ugly car here. It's my ugly car. Plain old ugly car here. These two vehicles are very different in terms of inertia. To get this big truck moving down the road, it takes, like if you ever get behind one, they speed up really slow and it seems like it takes them forever to get going because it's hard to get that much mass moving. Whereas this car can speed up a lot quicker because it's so small. Likewise, it's really hard to bring this truck to a stop. They need a more stopping distance because they're so heavy, it's hard to slow that down, whereas this car needs less distance. So this truck has more inertia the car has less inertia. All right. Thinking about inertia, here's some times that you observe inertia. So we're going to do a little mental imagining. Imagine that you're racing around a track on a go-kart, or maybe you're driving a car in a circle, or you're in the rolly chair and someone's pushing you in a circle. There are three basic times that you notice your inertia. It's when you speed up in a positive way. So like if you're sitting at rest, we'll just pretend with the rolly chair, it's easier to draw. So you're sitting at rest, and you're sitting here in said rolly chair, and someone gives you a big shove from this direction, what's going to happen is your body is probably going to kind of lurch backwards, and like your back and your head may actually kind of snap backwards as the chair moves forwards. What you just observed was your body not really wanting to move. Your body was wanting to stay still, but the chair was pushing you forwards. Now, accelerating in a negative way. So if you're bebopping along in your rolly chair and all of a sudden, someone from behind grabs it and they, stop your chair real fast, you might actually get thrown forwards this time and fall flat on your face. Why is that? Because you were moving and you wanted to keep on moving, but the chair, like the chair stopped, then it's your tendency to keep moving. This is one of the reasons that we wear seatbelts in cars, because if you're traveling in a car at 70 miles an hour on the interstate and your car comes to a sudden stop, your body is still going 70 miles an hour. What the seatbelt does is helps tie you to the car so that you slow down with it instead of getting thrown through the windshield. So, the same thing with the chair, just a much smaller example. The other time is when you go around curves. And if you think about it, if you're driving in a car and the car goes around a curve to the left, your body actually leans to the right. Or, if the car goes around a right curve, your body kind of leans to the left because your body is wanting to stay on this path right here, which is straight, but the car is going to the right and it leans you over like your body is attempting to stay on the path that it was going beforehand. Okay, so going back to Newton's first law, another way to think of his law is basically that if there's no net force on an object, then it will stay at a constant velocity forever. And keep in mind, if an object is not moving, then it still has a constant velocity. Its velocity is just zero. So, basically, without forces acting on objects, they would just do whatever they're doing. Like it would be kind of weird. If you threw a ball, you would go the opposite direction for eternity. So here's some more examples of inertia. If you're riding on a skateboard and you fly forward off the board when you hit a curb, like the skateboard comes to a sudden stop and then you go flying forwards. That's because your body was moving with the skateboard and it kept on moving when the skateboard stopped. While you're sitting in the back seat of a car that makes a hard right turn, you squish your sibling against the side of the door. I'll tell you a better way that I've experienced this one in my car is when I have something in the front seat and like it's in my bag or purse or something like that. And if I stop all of a sudden, the contents, like sitting beside me, the stuff that's right here in the seat go flying into the floor. Why? Because the car came to a sudden stop and that stuff had been moving at whatever speed. It didn't stop moving, so it kept going forwards. Or if you've ever left a drink or something sitting loose in your car, you forgot about it, set it on the console, and it slid somewhere while you were driving, that's inertia. Headrests are placed in your cars to prevent whiplash because here we have our car seat again, and you've got the headrest that sits up here, like it's a very boxy car seat. Well, it comes on down, whatever. And you sit here, here's your head. If you if you end up having something happen like someone rear ends your car and they send it forward very quickly, your head's gonna sling backwards and it's going to hit that headrest. If the headrest wasn't there, your head would sling further back and you would injure your neck. So the headrest isn't really so much for resting. All right, not too many more things happening. We're also going to start talking about balanced and unbalanced forces, okay? If you have balanced forces, it's when they add up to equal zero. It's back when we had the vectors, and basically vectors would cancel each other out. Here's an example. We have a book sitting on a table. So I'm going to draw. Here's our table. It's got a crooked leg. And here's our book right here. Here's the book. and the book is sitting on a table. It says there's a force of gravity pulling down on the book. So I'm going to draw that pulling down. But if you think about it, there has to be a force that's pushing back up on the book. Wait, what? Yes, there has to be a force pushing back up on the book. If this force wasn't right here going in the opposite direction, then what would happen is the book would be falling through the table and it would hit the floor below. So in order for the book to go nowhere, there has to be an equal and opposite force that's acting on this in order to not move it. That means that there is no net force on the book because these two things cancel out. And remember, Newton's first law said that something will stay at rest if there's no net force acting on it. And that's exactly what's happening right here. Okay, so now what if they're unbalanced forces? This is when they don't add up to equal 0 and there is a net force. Okay, so on this side, balanced forces, we could write net force equals 0 newtons. Okay, when you have balanced forces. When it's unbalanced, we have some sort of a net force. Net force equals some number of newtons. Well, that would be, what if we drop this book? So we have the book, right here's the book, and we just let it go. We drop it from 2 meters. What's going to happen this time is you're going to have your force of gravity that's pulling it down, but we don't have any force pulling it upwards. So what does it do? It falls, okay? Now, there might be a little bit of air resistance, all right? So you might get a little bit of air resistance depending upon the weight of your book and the size of it and all of that. But the gravity is going to be much greater than air resistance. I think we all know that that book is not just going to levitate. So therefore it falls and, we end up with movement. You need to know some different ways that we are going to label some of these forces. So what I have for you is basically a little table. And we're just going to fill in some different diagrams, and I'll show you what I mean over here. So, for example, we have a force that we're going to label as F app. And what that means is that it is an applied force. Okay, so like you push or pull on something. We're going to have F with a little g. That is the gravitational force, or the force of gravity. Okay. We're going to have Fn. This is called the normal force. And what the normal force is the normal force is always perpendicular to the surface that an object is up against. So for example, let's just use this for just a second. If this was a box sitting on the floor, then, the floor is pushing down, or the box is pushing down on the floor, but the floor has to be pushing up on the box. It's perpendicular to the surface. Now, if this box were being held up against a wall, so for example, you are pushing this up against a wall this way, you are pushing this way, well then the wall has to be pushing back. And we could draw the arrows the opposite way. Like I could draw this one going, however you want to do it. Let's see. We could equally draw this way, that the book is being pushed into the wall. Well, the wall has to be pushing this way. So the normal force would be here and the applied force would be here. Well, how do I figure that? Because if this doesn't basically answer back, then you're pushing this box through the wall. So the normal force is just a force that basically opposes motion in a direction that's perpendicular to the surface that you're sitting on. Then we have Ft. It's a capital T. This is tension force. You have Ft whenever something is hanging. So if this box right here was hanging from the ceiling, then in this string right here, you would have Ft. You would still have Fg pulling down on the box, but Ft would definitely be in the rope, the chain, or whatever you have it hanging from right here. In this case, you don't have a normal force because it's not sitting on a surface, but you would have tension. And if your rope isn't strong enough, then, basically gravity would overcome tension. The rope would snap and down goes the box. We had air resistance earlier, and how we're going to write that, it looks like fair, F air. That is just simply air resistance. So if we let this said box right here, if we snapped it and let it go, obviously gravity would be pulling it down, and there would be some air resistance acting back against it. we have F with a capital E. That is elastic force. What elastic force is probably exactly what it sounds like. Actually, this is a capital or a lowercase e. I'm looking at it now on my paper. You may see a capital E in some places. So what that is like if you snap a rubber band, like you pull it back and it rebounds and it hits you, like it clearly hits with some force. Bungees, people that go bungee jumping, there's elastic force in that as you stretch it out and then it pulls you back up. And our last force that we're going to have is F with a little f, and that is frictional force, or the force of friction. So let's go back to this box right here that's actually come in kind of handy to explain these things. If the box is being pushed across a floor, now this works with our first example. If you are pushing the box across a rough floor, maybe we're going to push it to the left. It doesn't say which way up here. And if the floor is rough, what that's going to do is generate a force going the opposite direction. Well, if we're pushing it to the left, we're going to label that as F-app because that is our applied force. And over here, we're going to have FF, which is our frictional force. Now, if you are not able to push it with an F-app that's big enough to overcome this, your box is going to go nowhere. Now, we could also label some other forces about this box. This box, if it's on the floor, is going to have FG, because here sits the floor. Looks like it was levitating. Here sits the floor. The box is pushing down with the force of gravity, and we are going to have a normal force pushing back up. Why is that? Because without it, the box would be moving down through the ground at the same time that it's moving to the left. Okay, now, for our other one, if we have a hockey player, this is going to be a really bad, like, stick figure hockey player. So here's our hockey player with a really long torso and some skates on. You like those skates? They look like little boats. I don't know. So here's our hockey player. Here's our hockey stick. This is really bad. Told you it would be. If they glide on frictionless ice at a constant velocity, what all could we label for our little red hockey player? I do not want that. Okay. First of all, this person is going to have FG. They're obviously, like, here's the ice. They have to have weight. Weight is pushing down. And unless they are moving down through the ice, Fn would have to be the same as Fg. The ice is pushing back up on the person. Okay, if it is frictionless ice, what that would mean for us is that basically this person has no net force. There's going to be nothing accelerating them. They're just simply going at a constant velocity. So there wouldn't be friction coming this way. Now, what it doesn't account for is, like, there could be air resistance if you've ever, gone like at a pretty fast clip, that you can have like wind against you. So pretty much the only thing steering this is going to be whatever push got them going in the first place. So like their initial pushing off of the ground with their foot would have propelled them forwards, and then they'll just have to keep moving. There's not going to be friction going this way. However, there might be a little bit of air resistance heading against them. Now, what you're going to do is you're going to look at pictures like this, and you are going to use your newfound information about the forces and their labels to figure out what these mean. And hopefully you can see this. This is FF, and we're asked to determine the net force. In order to determine the net force, you're just using your vector addition like we've done in the past. If this has a force going 30 to the left and a force going 30 to the right, and that's it, then what happens to these two things is they cancel each other out. And so we are going to end up with an object that has a net force of 0 newtons. So what if it's like this instead? What if we have 20 to the left and 30 to the right? Well, remember, when our vectors are going in opposite directions, we subtract. So 30 minus 20 would be 10. We have a net force of 10 newtons, and don't forget, anytime we can, we give directions. And it's fine to give a direction as right or left instead of east or west. So I would accept 10 newtons to the right or 10 newtons east. So what about this one? What about if there's more arrows? Then we start seeing what all cancels out and what doesn't. Whatever this object is has a gravitational force of 100 newtons and a normal force of 100 newtons. Well, do you know what these two things do to each other? They cancel each other out. So, the net force up and down is just zero. But there is an applied force of 30 newtons to the left. There's nothing on this side to cancel it out, so our net force will be 30 newtons left or 30 newtons west. So that's what you're going to do now. You're going to go to the practice problems and you're going to work with some of these. By the way, these are called free body diagrams. I think I had it right here. A free body diagram is our diagrams with our forces drawn in the different directions. So your homework is going to work with these free body diagrams. I'm asking you to draw some, and I think that's most of what I'm doing is asking you to draw some free body diagrams. This is not about your drawing skills. You've seen how ugly mine can be. So, just knock yourself out. If you can't draw a person very well, then you draw a blob and then you do the arrows associated to the blob or make the person look like a rectangle for all that matters, okay? Just do the best that you can.